Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the faint glow of the Milky Way stretching across the darkness. But what if I told you that everything visible to our eyes, every twinkling light, every distant galaxy, is just a fraction of what's really out there? The universe is vast beyond comprehension, filled with structures so enormous, so bizarre, they challenge everything we think we know about space and time. And here's the wildest part: some of these cosmic marvels are so distant, so enigmatic, that humanity may never reach them, no matter how advanced our technology becomes. Today, we're embarking on a journey to explore 25 of the most mysterious structures hidden in the fabric of the cosmos. These aren't just stars or galaxies, they're colossal formations that defy logic, bending the rules of physics as we understand them. Imagine walls of galaxies stretching billions of light years across, voids so empty they could swallow our entire cosmic neighborhood without a trace, and gravitational anomalies so powerful they twist space itself into knots. These aren't science fiction, they're real, and they're waiting for us to uncover their secrets. But why does any of this matter? Because every time we peer into the depths of space, we're not just mapping the universe, we're piecing together the story of our own existence. These enigmatic structures hold clues to the origins of everything, from the first flickers of light after the Big Bang to the forces that will shape the cosmos billions of years from now. So buckle up, we're about to dive into the unknown, exploring wonders that will leave you awestruck, questioning, and maybe even a little humbled by just how much is still out there, waiting to be discovered. Imagine a force so powerful it's pulling entire galaxies, including our own Milky Way, toward it at unimaginable speeds. Welcome to the Great Attractor, one of the universe's most baffling mysteries. Hidden behind a thick curtain of stars, dust, and gas in what astronomers call the zone of avoidance, this gravitational heavyweight has eluded direct observation for decades. Think of it like trying to spot a lighthouse through a blizzard, except this blizzard is made of cosmic material, and the lighthouse is tugging on everything around it with irresistible force. What makes the Great Attractor so intriguing isn't just its hidden location, it's the sheer scale of its influence. Scientists estimate it exerts a pull equivalent to tens of thousands of Milky Way galaxies combined. But what is it? Some theories suggest it could be a supercluster of galaxies so dense it warps spacetime itself. Others propose something even more exotic, a concentration of dark matter, that invisible glue holding the universe together, acting like a cosmic magnet on a grand scale. Then there's the wild card. Could it be a remnant of something ancient, a scar from the early universe we don't yet understand? Here's the twist: we might never get a clear answer. Because while telescopes like Hubble and Chandra have peered around the edges of the zone of avoidance, mapping the Great Attractor's shadowy outline, the heart of this enigma remains just out of reach. It's a reminder that even in an age of cosmic discovery, the universe still keeps its deepest secrets locked away. And that's what makes this journey so thrilling. Every mystery we uncover only reveals how much more is waiting in the dark. Now picture stepping into a void so vast it could swallow 10,000 galaxies like ours without a trace. That's the Boots Void, a cosmic desert stretching over 300 million light-years across. Unlike the crowded neighborhoods of most space, this region is eerily empty, with only a handful of galaxies scattered across its unimaginable expanse. To put that into perspective, if our Milky Way were placed inside it, our nearest galactic neighbor would be so far away, even its light would take tens of millions of years to reach us. It's like being stranded in an ocean with no land in sight, except the ocean is space itself, and the emptiness is almost unnatural. What makes the Boots Void so puzzling isn't just its size, it's the way it defies our understanding of how the universe should look. Based on the cosmic microwave background and simulations of the Big Bang's aftermath, matter should be distributed relatively evenly, like foam in a freshly poured beer. But this void is more like a sudden, gaping hole in that foam. So how did it form? Some theories suggest it could be the result of smaller voids merging over billions of years, like soap bubbles combining into one enormous cavity. Others propose something far stranger, that it's a fingerprint of an ancient collision between our universe and another, a scar left behind by a multiverse we can't yet see. Then there's the spine-chilling possibility that the boot's void isn't empty at all but filled with something invisible. Dark energy, the mysterious force accelerating the universe's expansion, might be concentrated here, pushing galaxies apart like an unseen hand clearing a table. Or perhaps dark matter, the invisible scaffold of the cosmos clumped here in a way that somehow repels ordinary matter. Whatever the truth, this void forces us to confront how little we really know about the universe's scaffolding. But here's the kicker: the boot's void isn't just a cosmic oddity, it's a clue. By studying these vast nothingnesses, astronomers are piecing together how the universe evolved, how gravity sculpted the cosmos over eons, and why some regions ended up crowded with galaxies while others became ghost towns. It's a reminder that sometimes the most revealing thing isn't what's there, but what's missing. And in that absence, we might just find the answers to questions we haven't even thought to ask yet. Some walls in the universe aren't made of brick or stone, they're woven from galaxies themselves, stretching so far they bend our understanding of reality. Enter the Hercules-Corona Borealis Great Wall, a galaxy filament so enormous it would take light 10 billion years to travel from one end to the other. To grasp that scale, picture this: if our solar system were a grain of sand, this structure would be the size of the entire North American continent. It's not just big, it's impossibly big, challenging one of cosmology's foundational rules, the idea that on large scales, the universe should look roughly the same no matter where you are. Discovered in 2013 by mapping gamma-ray bursts, the universe's brightest fireworks, this Great Wall defies expectations. These bursts act like cosmic breadcrumbs, revealing concentrations of matter we can't see directly. And what they've shown is startling. The Hercules-Corona Borealis Great Wall isn't just a cluster of galaxies. It's a sprawling, ribbon-like structure, a remnant of the universe's infancy when gravity's fingertips sculpted matter into vast, interconnected webs. But here's the problem: according to our current models, nothing this colossal should have had time to form so early in cosmic history. It's like finding a skyscraper in the middle of the Stone Age. Something's missing from our timeline. Studying it is like trying to trace the outline of a mountain while standing at its base. The wall's sheer size means parts of it lie beyond our observational horizon, the point where the universe's expansion outpaces light itself. Even its distance plays tricks on us. As we peer deeper into space, we're also looking further back in time, seeing the wall not as it is today, but as it was when the universe was barely half its current age. This time capsule effect forces astronomers to wrestle with dizzying questions. Did this structure form through some unknown gravitational anomaly? Could it be a flaw in our measurements, or worse, a crack in the cosmological principle itself? Yet for all its mystery, the Hercules-Corona Borealis Great Wall isn't just a scientific headache, it's a gift. By pushing our models to the breaking point, it reveals where our knowledge ends and the real frontier begins. Every time we think we've mapped the cosmos, the universe throws another curveball, reminding us that the greatest discoveries aren't just about finding answers, they're about learning how much we've yet to ask. Some galaxies spiral, some collide, but one stands alone in cosmic perfection. Hoag's object is a celestial oddity so flawless it could pass as a piece of abstract art. A shimmering blue ring of young stars encircling a golden core, separated by an almost empty gap as if drawn with a compass. Discovered in 1950 by astronomer Arthur Hoag, this ring galaxy defies typical galactic shapes, leaving scientists puzzled over how something so symmetrical could emerge from the chaos of the universe. The mystery begins with the ring itself, a sparkling band of stellar nurseries where massive blue stars burn bright, their light tracing a circle nearly 120,000 light-years across. At its center sits an older, yellower population of stars, calm and dense like a miniature elliptical galaxy, but between them almost nothing. No twisting arms, no warped disk, no bridge of matter connecting the two. It's as if the universe carved out this pristine structure with deliberate precision. So how does something like this form? Most ring galaxies, like the famous Cartwheel Galaxy, are born from violent collisions, one galaxy punching through another, sending shockwaves through interstellar gas that trigger star formation in circular ripples. Yet Hoag's object shows no signs of a recent impact, no debris trail or distorted neighbor hinting at cosmic violence. Alternative theories suggest it might be the result of an ancient instability, perhaps a bar-shaped structure of stars that dissolved eons ago, flinging material outward into that perfect ring. Others propose an even wilder idea, a peanut-shaped galactic core that funneled gas into orbit, igniting star formation in this precise, isolated loop. What makes Hoag's object even more extraordinary is its solitude. Unlike most galaxies which cluster in groups, this ringed wonder floats alone in a quiet patch of space, untouched by gravitational interference for billions of years. That isolation raises provocative questions. Is this a frozen moment in galactic evolution, a snapshot of a fleeting phase most galaxies pass through unseen? Or is it a cosmic fluke, a structure so rare we might never find another like it? Peering at it feels like uncovering a relic. Light from Hoag's object has traveled 600 million years to reach us, meaning we see it as it was before the first fish crawled onto land. Back then, its ring might have blazed with newborn stars, while its core glowed with the quiet light of aging suns. Today, its fate remains uncertain. Will the ring eventually fade, its stars dispersing into the void, or will fresh gas spiral inward, reigniting the cycle of starbirth? Perhaps the most humbling lesson of Hoag's object is how much we still don't understand about galactic life cycles. In a universe dominated by spirals and ellipticals, this perfect ring whispers of roads not taken, of how differently galaxies might evolve under just the right conditions. It's a reminder that for every rule we think we've uncovered, the cosmos keeps an exception waiting in the dark. The universe isn't just expanding, it's dragging entire galaxy clusters along for the ride, defying everything we thought we knew about cosmic motion. This is the dark flow, a phenomenon so bizarre it feels like the cosmos is playing a trick on us. Picture hundreds of massive galaxy clusters, each containing thousands of galaxies, all drifting in the same direction at breakneck speeds, like leaves caught in a river no one can see. The odd part, there's no obvious source for this motion. No supercluster, no great attractor, nothing in the observable universe powerful enough to explain it. When astronomers first detected this coordinated movement in 2008, it sent shockwaves through cosmology. Using the cosmic microwave background, the afterglow of the Big Bang, as a reference frame, they tracked the motion of galaxy clusters across billions of light years. The results were unsettling. These clusters weren't just moving randomly with the universe's expansion. They were being pulled toward a single patch of sky near the constellations Centaurus and Vela at speeds exceeding 2 million miles per hour. It's as if space itself has a current and everything's being swept along. So what's behind this cosmic tug of war? One spine-tingling possibility is that the dark flow originates beyond the edge of our observable universe. Think of it like standing on a beach feeling a strong undertow. You can't see the source, but you know something massive must be pulling the water. In this case, that something could be a concentration of mass so enormous it warps space-time on a scale we can't comprehend, perhaps leftover from a collision between universes in the multiverse. Or maybe it's evidence of a flaw in Einstein's theory of gravity, a crack in relativity that only reveals itself at the largest scales. Not everyone's convinced, of course. Skeptics argue the dark flow might be a measurement error, an artifact of how we interpret the cosmic microwave background. Others suggest it could be the lingering influence of inflation, the universe's explosive growth spurt after the Big Bang stretching spacetime unevenly like wrinkles in a rug. But if the dark flow is real, it forces us to confront an uncomfortable truth. There's far more to the cosmos than what we can observe. The structures shaping our universe might extend into regions forever hidden from view, their gravity reaching across the void to tug at everything we can see. Here's what makes the dark flow truly humbling. If confirmed, it wouldn't just add another mystery to the list, it would rewrite the rules. Suddenly, the universe isn't a self-contained bubble. It's a single room in an endless mansion, with forces from unseen hallways rattling the doors. And that's the thrill of cosmology. Every anomaly, every deviation from expectation, is a signpost pointing to deeper truths. The dark flow doesn't just challenge our maps of the cosmos, it suggests we've only been charting the shoreline while the vast ocean lies undiscovered. Rising from the heart of our galaxy like twin titans, the Fermi Bubbles stretch 50,000 light-years above and below the Milky Way's core, an invisible pair of cosmic balloons glowing with gamma rays. Discovered in 2010 by NASA, a Fermi Gamma Ray Space Telescope, these colossal structures remained hidden for so long because human eyes can't see their high-energy light. But with the right instruments, they reveal themselves as a breathtaking spectacle. Two vast lobes of superheated gas, charged particles, and magnetic fields, each large enough to contain 15 Milky Ways stacked end to end. What's startling isn't just their size, it's their violence. The bubbles' gamma rays betray the presence of particles moving near light speed, suggesting some cataclysmic event rocked our galaxy's center millions of years ago. But what could unleash such energy? One leading theory points to Sagittarius, a star, the supermassive black hole at the Milky Way's core. Imagine a black hole gorging itself on a colossal meal, perhaps a dense gas cloud or even a wayward star, before belching out jets of radiation and matter with enough force to punch through galactic gas like a double-sided cannon blast. These jets might have inflated the bubbles over centuries, leaving behind this lingering glow. Yet there's another contender, a frenzy of star formation so intense it became self-destructive. Picture hundreds of massive stars igniting simultaneously near the galactic center. Their fierce winds and eventual supernova explosions could have combined into a tsunami of energy, blowing bubbles in the surrounding gas like a child puffing soapy rings. Supporting this idea are observations of starburst galaxies, where similar processes create smaller, though no less violent, structures. The weirdest part: these bubbles might be ephemeral. Simulations suggest such features eventually fade, their energy dissipating into the wider galaxy. That raises a tantalizing possibility. We might be catching them at a special moment, like spotting the last embers of a fireworks display that lit up the sky long before humans walked the Earth. But the Fermi Bubbles are more than relics, they're a cosmic laboratory. Their edges act like particle accelerators, colliding matter in ways we can't replicate on Earth. Studying them could reveal how galaxies distribute energy, how black holes shape their surroundings, and even how cosmic rays, mysterious high-speed particles that constantly bombard Earth, are born. Perhaps their greatest lesson is humility. Something monumental happened in our galactic backyard, and we missed it, not by years or centuries, but by millennia. It's a reminder that the cosmos doesn't operate on human timescales, and the galaxy's most dramatic performances often unfold in the dark, waiting for the right moment to flicker back into view. Deep in the cosmic dark, where the universe was still young, vast clouds of hydrogen glow with a light so intense it defies explanation. These are the Lyman-Alpha Blobs, enigmatic structures spanning hundreds of thousands of light-years, their namesake radiation painting the early cosmos with an eerie ultraviolet hue. Imagine a celestial fog so luminous it outshines entire galaxies, yet so diffuse it's nearly transparent. First detected in the late 1990s, these blobs are like cosmic lighthouses, beaming signals from a time when the universe was less than 2 billion years old, a fraction of its current age. What makes these blobs so baffling isn't just their size or brightness, it's the mystery of their power source. Lyman-alpha radiation occurs when electrons in hydrogen atoms drop to a lower energy state, releasing that distinctive ultraviolet glow. But here's the puzzle. The energy required to excite this much hydrogen across volumes larger than galaxy clusters would demand an almost unimaginable outpouring of radiation. Yet when astronomers peer into these blobs, they often find no obvious engines, no bustling galaxies or quasars bright enough to explain the fury. It's like stumbling upon a city lit by invisible floodlights with no power plant in sight. One theory suggests these blobs might be cosmic nurseries on a grand scale, where the universe's first giant galaxies were forged. Picture rivers of cold gas funneled by the gravitational pull of dark matter, collapsing into star-forming frenzy. The newborn stars, especially massive ones burning hot and fast, could flood the surrounding gas with ultraviolet light, energizing the hydrogen into that pervasive glow. Supporting this idea are faint galaxies often spotted nesting inside the blobs, their starlight too dim to account for the radiance but hinting at a symbiotic relationship. Another possibility is even more dramatic. The glow could be fueled by supermassive black holes in their infancy, devouring matter and spewing energy before they're fully formed. These primordial black holes might have been messy eaters, their radiation inflating the blobs like glowing balloons. Or perhaps the hydrogen itself is acting as a cosmic screen, scattering light from distant quasars in a way that makes the entire structure shimmer, like mist catching the glow of a faraway street lamp. The true significance of Lyman-Alpha Blobs lies in what they reveal about the universe's chaotic adolescence. They're snapshots of an era when gas was the dominant player before galaxies had fully taken shape. By studying them, astronomers trace how raw material was distributed and how gravity began sculpting the cosmos into the structured universe we see today. Yet for all they've taught us, these blobs remain stubbornly elusive. Their light, stretched by the expansion of the universe, arrives faint and redshifted, requiring the world's most powerful telescopes just to glimpse them. And because they're so ancient, we'll never see them as they are now, only as they were when the cosmos was still in its cradle. That's the bittersweet irony of cosmology. The further we look, the more we realize how much is forever out of reach. The Lyman-Alpha Blobs are cosmic ghosts. Their glow a whisper from a time when everything was just beginning. And in that whisper, we might finally hear how the universe learned to shine. Stretching nearly 1.4 billion light-years across the cosmic canvas, the Sloan Great Wall stands as a titan among galactic structures. A sprawling filament of superclusters so vast it could contain tens of thousands of Milky Ways laid end to end. Discovered in 2003 by mapping galaxies from the Sloan Digital Sky Survey, this megastructure isn't just big, it's improbably big, challenging one of astronomy's bedrock assumptions, the cosmological principle which states that on large scales, the universe should appear roughly uniform no matter where you look. Yet here's a wall that defies that expectation, a cosmic thread so thick and dense it resembles a seam stitching the universe together. What makes the Sloan Great Wall extraordinary isn't just its size, it's the way it forces us to rethink how matter organizes itself. Imagine dumping sand onto a table and expecting it to spread evenly, only to watch it inexplicably pile into a single, towering ridge. That's the puzzle here. According to our best models of cosmic evolution, gravity's pull should have distributed galaxies more uniformly over billions of years. Instead, we find this jaw-dropping concentration, a structure so massive it contains multiple superclusters, each themselves groupings of thousands of galaxies bound together like beads on an invisible string. So why aren't such megastructures more common? The answer might lie in the delicate balance between gravity and dark energy. In the universe's youth, gravity had free rein to clump matter together, sculpting filaments and walls like this one. But as dark energy's repulsive force began dominating cosmic expansion around 5 billion years ago, it started stretching space itself, effectively putting the brakes on the growth of new colossal structures. The Sloan Great Wall, then, could be a relic of a bygone era, a time when the universe was still small enough for gravity to weave such grand tapestries before dark energy pulled the threads apart. Yet even among giants, the Sloan Great Wall is an outlier. Later surveys revealed even larger structures like the Hercules-Corona Borealis Great Wall, but none have matched its iconic status. Part of its rarity comes down to sheer luck, the right density of matter in the right place at the right time, like a cosmic lottery winner. But it's also a testament to how hard these structures are to spot. Mapping something this immense requires painstakingly cataloging millions of galaxies across vast swaths of sky, a needle-in-haystack search where the needle is itself light-years wide. The wall's discovery was a watershed moment, proving that the universe's largest structures could hide in plain sight. Today, it serves as both a benchmark and a warning, a reminder that our assumptions about the cosmos are always provisional, waiting for the next revelation to append them. And perhaps that's the most profound lesson of all. In a universe still writing its own rules, the biggest surprises might still be lurking just beyond the edge of our maps. At the heart of the Phoenix Cluster, a sprawling metropolis of galaxies over 5.7 billion light-years away, lurks a monster, a supermassive black hole shattering every record we thought we knew. This isn't just another galactic anchor, it's a cosmic furnace so voracious it devours the equivalent of 60 suns every year, heating the surrounding gas to millions of degrees and firing jets of plasma hundreds of thousands of light-years into space. To grasp its power, picture a hurricane spinning at the center of an ocean, churning the waters so violently it permanently alters the sea's chemistry. Except here, the ocean is intergalactic space, and the hurricane's winds are torrents of raw energy bending reality itself. What makes this black hole extraordinary isn't just its appetite, it's the way it refuses to play by the rules. Most supermassive black holes cycle between feasting and fasting, their activity flickering like a campfire. But the Phoenix Cluster's titan burns with relentless fury, a perpetual storm of accretion. Its accretion disk, the swirling maelstrom of doomed matter, glows brighter than entire galaxies, while twin jets erupt from its poles at near light speed, carving cavities in the surrounding gas so vast they could swallow our solar system 1,000 times over. These jets aren't just spectacular, they're transformative. As they slam into the cluster's gas, they trigger shock waves that ripple across millions of light-years, scattering heavy elements like cosmic seeds and stirring the primordial soup from which new galaxies might one day form. Yet the real enigma lies in the black hole's paradoxical role, destroyer and architect. Normally, black holes this active should overheat their surroundings, stifling star formation by blowing gas away like leaves in a gale. But here, observations reveal something astonishing: pockets of gas cooling rapidly enough to birth stars despite the chaos. It's as if the black hole's fury inadvertently builds sanctuaries amid the storm, where gravity can quietly knit new suns from the wreckage. This delicate balance challenges our understanding of feedback loops, the invisible dials regulating how black holes and galaxies grow together. The implications stretch far beyond this single cluster. If such behemoths are common in the early universe, they could explain how the first galaxies grew so quickly, their black holes acting like cosmic forges, hammering raw gas into stellar factories. Or perhaps the Phoenix Cluster is an outlier, a rare glimpse of what happens when a black hole's hunger goes unchecked. Either way, it forces us to confront a humbling truth. For all their destructive might, black holes might be the universe's ultimate sculptors, carving the voids and sparking the fires that shape everything we see. And somewhere in that paradox between annihilation and creation, we might finally find the missing link in the story of how the cosmos builds itself. Hanging in the void like a celestial smile, the giant arc is a structure so enormous it seems to mock our understanding of cosmic scale. This recently discovered crescent of galaxies stretches 3.3 billion light-years across, so vast that if you could travel at light speed, it would take you longer to cross it than Earth has existed as a planet. Discovered in 2021 by analyzing the light of quasars, this formation isn't just big, it's impossibly big, defying one of astronomy's core beliefs, that matter should be spread evenly across the universe at the largest scales. What makes the giant arc so disruptive isn't just its size, it's the way it shouldn't exist at all. According to the cosmological principle, the universe ought to look roughly the same no matter where you're observing from, like a perfectly mixed cake batter. Yet here's a wrinkle in that smoothness, a gathering of galaxies so dense it forms a curve spanning roughly 1/15 the entire observable universe. Imagine stirring a cup of coffee only to find all the grounds clustered into a single, unbroken ring. That's the level of cosmic incongruity we're dealing with. How does something this colossal form? One theory points to Baryon acoustic oscillations, sound waves left over from the universe's infancy that might have frozen into the distribution of matter like ripples in a pond. But even these primordial echoes shouldn't produce structures this gigantic. Another possibility is that dark matter, the invisible skeleton of the cosmos, somehow pooled in this region, pulling galaxies into its gravitational wake like iron filings to a magnet. Or perhaps the giant arc is a fossilized imprint of an ancient cosmic collision, a scar from when our universe was still entangled with others in the multiverse. The irony is that we're seeing the giant arc as it was 9 billion years ago, a snapshot frozen in time when the universe was far younger. Today, its galaxies might have drifted apart, their connections stretched thin by dark energy's relentless push. But its very existence forces us to ask, are we missing something fundamental about how gravity works on the grandest scales? Or worse, could the cosmological principle itself be flawed? For astronomers, the giant arc isn't just a curiosity, it's a litmus test. If structures like this are common, they could rewrite our models of cosmic evolution, revealing a universe far lumpier and more unpredictable than we ever imagined. And if they're rare, that's even stranger. Why would the cosmos assemble such a wonder in one place and nowhere else? Either way, the giant arc stands as a humbling reminder. The universe isn't just bigger than we know, it's weirder. And every time we think we've mapped its edges, it throws another curveball, daring us to look deeper. Tucked away in the cosmic microwave background, the afterglow of the Big Bang, lies a mystery so chilling it's literally called the cold spot. This patch of sky, spanning nearly 2 billion light-years, registers significantly colder than its surroundings, as if the universe left a freezer door ajar in one corner of creation. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, this anomaly isn't just a statistical blip. It's a full-blown cosmic detective story, with theories ranging from the mundane to the mind-bending. At first glance, the cold spot might seem like a simple void, a vast, underdense region where fewer galaxies mean less gravitational pull, causing light passing through to lose energy and appear cooler, an effect known as the integrated Sachs-Wolf effect. But here's the twist: when astronomers mapped the area, they found the void explanation falls short. The required emptiness would need to be so extreme, so unrealistically sparse. It's like finding a desert larger than all known deserts combined. That's when the plot thickens. Enter one of the most electrifying possibilities. The cold spot could be a bruise left by a collision with another universe. In the multiverse theory, our cosmos isn't alone. It's one bubble in an endless froth of universes, each with its own physics. If a neighboring universe once bumped into ours, the energy exchange might have left a temperature dent in the cosmic microwave background, like a fingerprint on a foggy mirror. The idea is controversial, to say the least. Critics argue it's untestable, a cosmic, just-so story. Yet supporters point out the cold spot's shape and location align eerily well with what such a collision might look like. Then there's the wild card, primordial physics gone wrong. Some theorists suggest the cold spot might be a relic of exotic phase transitions in the early universe, moments when the very fabric of space-time reconfigured itself, leaving behind defects akin to cracks in ice. These cosmic texture defects could, in theory, create localized temperature variations, but detecting them would require evidence we don't yet have. What makes the cold spot so compelling isn't just its origin story, it's the way it forces us to question the limits of our knowledge. If it's a void, it challenges our understanding of how matter clumps. If it's a multiverse signature, it rewrites our place in reality. And if it's neither, that might be the most exciting outcome of all, a signpost pointing to physics we've yet to dream of. For now, the cold spot remains an enigma wrapped in microwaves, a cosmic Rorschach test revealing as much about our curiosity as it does about the universe. Every time we think we've pinned it down, it slips away cold, distant, and tantalizingly opaque. And perhaps that's the lesson. The universe's greatest mysteries aren't just puzzles to solve, but invitations to keep looking further. Hidden in the constellation Monoceros, about 2,300 light-years from Earth, lies a cosmic jewel so precise it looks crafted by celestial architects, the Red Rectangle Nebula. This stunning structure defies the usual chaos of stellar death, presenting itself not as a tattered cloud or swirling vortex, but as a near-perfect geometric figure, its nested rectangles glowing with an eerie crimson hue. Named for its appearance in early telescopic images, this nebula isn't just a visual oddity, it's a masterclass in how binary stars can sculpt the universe in ways single stars never could. At the heart of the red rectangle, two stars perform a gravitational tango, locked in a tight orbit that shapes everything around them. The primary star is a dying red giant, shedding its outer layers in a last, desperate exhale. But here's where things get fascinating. Its companion star isn't just a passive bystander. It's an active participant, channeling those ejected gases into two vast cones that beam outward like cosmic headlights. Because we're viewing this system almost edge-on, those cones overlap, creating the illusion of nested rectangles. It's like watching a spinning firework from the side, its sparks confined to a precise, angular pattern by unseen forces. The nebula's vivid color comes from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons, which fluoresce under ultraviolet radiation from the central stars. These molecules aren't just pretty, they're cosmic clues. The red rectangle's dust is unusually rich in complex organic compounds, the kind that could one day seed new planets or even life. Some scientists speculate this nebula might be a factory for probiotic chemistry, churning out ingredients that, under the right conditions, could eventually form the building blocks of biology. Yet the real magic lies in the physics of symmetry. Most planetary nebulae, the glowing shells of dying stars, are messy, asymmetrical affairs, their shapes warped by chaotic stellar winds or magnetic fields. The red rectangle's precision suggests something far more orderly, a stellar partnership so balanced that gas and dust are funneled with almost mathematical precision. This isn't just random stellar death, it's stellar death with a blueprint, but perfection like this can't last. In a few thousand years, the red rectangle's delicate structure will dissipate, its gases scattering into interstellar space. What remains will be a cooling white dwarf and its companion, orbiting silently in the dark. For now, though, this nebula stands as a fleeting masterpiece, a reminder that even in the vast, unruly cosmos, there are moments and mechanisms that produce near miraculous order. And in that order, we might just find the secrets to how complexity arises from chaos. Imagine a galaxy so precise it acts as a cosmic ruler, helping astronomers measure the vast scales of the universe with unprecedented accuracy. That's NGC 4258, a spiral galaxy 23 million light-years away with a secret hidden in its core, a colossal disk of water vapor spinning around a supermassive black hole, firing off laser-like beams of radiation known as megamasers. Unlike regular lasers that rely on light, these masers are powered by microwave emissions, and they're so finely tuned they rival the precision of atomic clocks. At the heart of this phenomenon lies a black hole weighing 40 million suns, surrounded by a disk of gas and water molecules stretched into a warped, twisted shape. Normally, such disks are flat, like vinyl records spinning smoothly around a central spindle. But NGC 4258's disk is bent like a vinyl record left too long in the sun, its outer edges tilting dramatically as they spiral inward. This distortion isn't just a curiosity, it's a clue. The warping likely comes from the black hole's gravitational tug of war with its surroundings, or perhaps from jets of material punching through the disk like cosmic blowtorches. Either way, it's a rare window into how black holes interact with their environments over cosmic time. But the real magic of this galaxy lies in those water vapor masers. Picture water molecules floating in the disk, each one acting like a tiny radio transmitter. As they orbit the black hole, some move toward us, their signals squeezed into higher frequencies, while others move away, their signals stretched into lower tones. By mapping these shifts, astronomers have pinpointed the disk's rotation with mind-bending precision, calculating distances across the universe to within a few % error, a feat akin to measuring the width of a human hair from 10 miles away. This makes NGC 4258 a cornerstone in the cosmic distance ladder, the toolset we use to gauge the scale of everything from nearby stars to the edge of the observable universe. What's astonishing is how this galaxy defies expectations. Most megamasers are chaotic, their signals scrambled by turbulent gas. But here, the disk's orderly motion despite its warp creates masers so stable they've become the gold standard for cosmic measurements. It's like finding a perfectly balanced gyroscope in the middle of a hurricane. The lessons from NGC 4258 ripple far beyond its borders. Its warped disk challenges assumptions about how black holes feed, suggesting that even the most violent cosmic engines can leave delicate fingerprints on their surroundings. And those masers, they're more than tools, they're proof that sometimes the universe hands us a gift wrapped in water vapor and microwaves, a natural wonder so precise it helps us map the heavens themselves. In a cosmos full of chaos, this galaxy stands as a rare beacon of order, whispering secrets about the machinery that shapes space-time. The universe holds its secrets tightly, and none cling to mystery quite like dark matter halos, vast, invisible cocoons enveloping galaxies in a gravitational embrace we can't see but can't ignore. Picture a galaxy like our Milky Way not as a solitary island of stars, but as the glittering tip of an iceberg, with 90% of its mass hidden beneath the surface in this shroud of enigmatic particles. These halos don't emit light, reflect it, or interact with ordinary matter in any way except through gravity, making them cosmic ghosts haunting the architecture of the cosmos. What makes dark matter halos so pivotal isn't just their invisibility, it's the way they sculpt the universe. Without their gravitational scaffolding, galaxies would fly apart, their stars scattering like marbles dropped on a tile floor. Take the Andromeda Galaxy, our nearest spiral neighbor. Its visible disk spins so fast that, by conventional physics, it should have torn itself apart eons ago. The only explanation, an immense unseen mass 10 times greater than all its stars and gas combined anchoring it in place. That's the power of a dark matter halo, an unseen hand steadying the cosmic scales. Yet the deeper we probe, the stranger these halos become. Simulations suggest they aren't smooth clouds but lumpy, with dense subhalos orbiting inside them like unseen moons. Some theorists propose these clumps could host their own dwarf galaxies, invisible except for the faintest gravitational tugs on their visible neighbors. Others speculate that dark matter particles might collide in the halo's core, annihilating in bursts of gamma rays. A hypothetical signal scientists have hunted for decades, like listening for whispers in a thunderstorm. The frustration and fascination of dark matter halos lies in their contradictions. They're ubiquitous, shaping everything from the tiniest galaxies to the largest superclusters, yet we've never directly detected a single particle of their substance. They're universe builders, yet cosmic phantoms, and perhaps most intriguingly, their existence hints at physics beyond the standard model, a shadow realm of particles and forces utterly alien to everything we know. So why does this matter to anyone but astronomers? Because dark matter halos are more than cosmic curiosities, they're keys to our origins. The way they funneled gas into the early universe's first galaxies likely determined where stars ignited, where planets formed, and ultimately where life could arise. In tracing their invisible contours, we're not just mapping the unseen, we're uncovering the blueprint of existence itself. And until we solve their riddle, the universe will keep its greatest architect hidden in plain sight. Some galaxies grow quietly, nurturing stars over eons, but NGC 1316 takes a darker path. This cosmic predator, lurking 60 million light-years away in the constellation Fornax, earned its nickname, the Cannibal Galaxy, through a history of violent mergers, its twisted arms and swirling dust lanes bearing the scars of past feasts. What makes this galaxy extraordinary isn't just its appetite. It's the way its chaotic structure reveals how galaxies evolve not through gentle growth, but by tearing their neighbors apart and stitching the pieces into something new. Peer closely at images of NGC 1316 and you'll notice something unsettling. Its core is surrounded by a chaotic web of dark dust lanes, while streams of stars stretch outward like frayed ribbon. These aren't the elegant spiral arms of a typical galaxy. They're debris trails, evidence of at least two major collisions in the last few billion years. Picture two massive galaxies, each brimming with billions of stars, slamming together in a gravitational tug-of-war so fierce it warps their shapes beyond recognition. The loser gets shredded, its stars scattered into tidal tails, while the victor NGC 1316 grows larger, its gravity weaving the stolen material into a monstrous new form. But the violence doesn't stop there. Deep within its core, the galaxy harbors one of the most powerful supermassive black holes known, a beast likely fattened by the influx of gas and stars from its mergers. As fresh material spirals inward, the black hole erupts in bursts of radio waves, making NGC 1316 one of the brightest radio sources in the southern sky. These jets, visible only to specialized telescopes, reveal the ongoing turmoil. Even as the galaxy devours its prey, the energy unleashed in the process shapes its future, heating surrounding gas and potentially stifling new star formation. What's fascinating is how cannibal galaxies like this one challenge our ideas of cosmic evolution. For decades, astronomers assumed galaxies grew primarily by slowly accreting gas, forming stars in orderly waves. But NGC 1316 proves mergers are just as vital, perhaps even more so for the universe's most massive galaxies. Every collision injects chaos, stirring up gas clouds to ignite frenzied starbursts, while gravitational shocks funnel material toward black holes, feeding their fury. It's a cycle of destruction and rebirth where galaxies don't just grow, they're forged in the furnace of cosmic collisions. Yet NGC 1316 holds another secret, its globular clusters. Most galaxies host ancient, densely packed groups of stars called globulars, but here they're strangely sparse and unevenly distributed, the likely culprit. Those same mergers, as incoming galaxies were torn apart, their globular clusters were either absorbed, flung into intergalactic space, or dissolved entirely, leaving behind a scattered trail of stellar orphans. This mismatch is like finding a city where half the neighborhoods vanished overnight, their bricks repurposed into new towers, The ultimate lesson of NGC 1316 isn't just about destruction, it's about transformation. With every merger, the galaxy reinvents itself, its structure and fate rewritten by forces far beyond the sum of its parts. And somewhere in that chaos lies a truth about our own Milky Way, which too will collide with Andromeda in billions of years. When that day comes, we'll witness firsthand the violent, creative power that shaped the cannibal galaxy, a reminder that even in the tranquil depths of space, the cosmos thrives on upheaval. Floating through the cosmos like spectral smudges, the vorwerps, Dutch for little objects, are ghostly green clouds of gas lit up by light that hasn't reached them in millennia. These cosmic afterglows, first discovered by schoolteacher Hanny van Arkel while participating in the Galaxy Zoo project, glow with an eerie luminescence, their oxygen-rich gas ionized by radiation from quasars, supermassive black holes in galaxies that once raged like celestial infernos but have since fallen silent. The result, a time-delayed snapshot of violence, where the light we see today reveals outbursts that actually occurred tens of thousands of years ago, like stumbling upon the glowing embers of a campfire whose flames died out before humans built the first cities. What makes the vorwerps so valuable isn't just their haunting beauty, it's their role as cosmic coroners telling the story of a quasar's death. When a supermassive black hole feasts on surrounding gas, it doesn't just swallow matter. It belches out torrents of radiation powerful enough to ionize gas clouds millions of light years away. But quasars are fickle beasts, flickering on and off as their fuel supply waxes and wanes. By the time the quasar shuts down, the light from its final feast is still traveling through space, illuminating clouds like the vorwerps long after the black hole has gone quiet. It's as if the universe handed us a collection of black hole obituaries written in neon green gas. The most famous of these objects, Hani's vorwerp, named after its discoverer, dangles near the spiral galaxy IC 2497 like a phantom limb. The galaxy's central black hole, once a brilliant quasar, is now a shadow of its former self, yet its vorwerp still glows, a testament to the quasar's past fury. But here's the twist: the gas cloud isn't just a passive billboard. Its turbulent structure suggests it was shaped by the quasar's winds, sculpted into intricate filaments and bubbles by forces that once rivaled supernova in their violence. This makes vorwerps more than fossils, they're kinetic art, frozen in the act of being carved by invisible hands. Yet the real revelation lies in what these objects tell us about black holes on off switches. By studying multiple vorwerps, astronomers have pieced together a startling truth. Quasars don't fade gently, they shut off abruptly like a cosmic breaker being flipped. Some vorwerps even show evidence that their quasars may have turned back on after a hiatus, suggesting that black holes cycle through periods of gorging and fasting on timescales far shorter than anyone expected. This isn't just academic. It reshapes our understanding of how black holes influence their host galaxies over cosmic time, alternating between nurturing star formation and snuffing it out with their radiative fury. But the most tantalizing question remains unanswered. How many more of these ghosts are lurking in the darkness, unlit by any quasar's glow? Vorwerps we can see are the lucky ones caught in the spotlight of a fading beacon. Others might drift unseen, their stories lost in the void. And that's the bittersweet lesson of these green wisps sometimes. The most revealing relics are the ones that only shine after the show is over. In the grand cosmic dance, galaxies don't just drift alone, they collide, merge, and reshape each other in violent, breathtaking transformations. And one of these collisions has our name on it. 4 billion years from now, the Milky Way will meet its destiny in a head-on embrace with the Andromeda Galaxy, our closest spiral neighbor, currently hurtling toward us at 250,000 miles per hour. This won't be a gentle handshake, it'll be a slow-motion car crash spanning hundreds of millions of years, a celestial ballet where gravity twists stars, gas, and dust into an entirely new galactic structure. What makes this inevitable merger so fascinating isn't just the scale, it's the sheer improbability of stellar collisions. Despite Andromeda's trillion stars and the Milky Way's 300 billion, the vast distances between stars mean direct impacts will be vanishingly rare. Instead, the real drama will unfold in the gravitational chaos. Picture the two galaxies first swinging past each other, their mutual pull stretching long tendrils of stars into looping tidal tails like strands of cosmic taffy pulled apart. Over multiple passes, their spiral arms will shred, scattering stars into a chaotic halo. Meanwhile, their supermassive black holes, each weighing millions of suns, will begin a spiraling death spiral at the center, eventually merging in a burst of gravitational waves powerful enough to ripple spacetime itself. Yet the most striking change will be the sky itself. As Andromeda looms closer, it'll swell from a faint smudge into a dazzling disk covering half the night sky, its dust lanes and star clusters visible to the naked eye. During the merger's peak, new stars will ignite in brilliant blue bursts as compressed gas clouds collapse, while older stars are flung into intergalactic space like sparks from a forge. By the end, the Milky Way and Andromeda will have dissolved into a single, football-shaped elliptical galaxy, dubbed Milkdromeda by astronomers, a glowing relic of the two spirals that once were. The irony, while we can simulate this collision's broad strokes, the details remain maddeningly uncertain. For instance, our galaxy's smaller neighbor, the Triangulum Galaxy, might join the fray, turning a duel into a chaotic three-body interaction. Gas dynamics, how clouds fragment and ignite new stars, defy precise modeling, leaving the merger's stellar fireworks poorly understood. Even our own solar system's fate is unclear. There's a small chance we could be flung into intergalactic space, left adrift in the freezing void, though more likely, we'll simply orbit farther from the chaotic core. What's humbling is realizing this isn't some rare catastrophe, it's business as usual for galaxies. Hubble observations reveal similar mergers everywhere in the early universe, proving galaxies grow by consuming each other. The Milky Way itself bears scars of past cannibalism, its halo littered with remnants of dwarf galaxies it absorbed long ago. Andromeda's even more voracious, its outskirts strewn with the corpses of smaller galaxies it's already devoured. Our future collision isn't an anomaly, it's a rite of passage for galaxies, a step in their evolution from modest spirals to bloated ellipticals. Yet for all its inevitability, the merger remains a reminder of how dynamic the cosmos truly is. We think of galaxies as eternal, unchanging, but they're living structures constantly reshaped by gravity's relentless hand. And while humanity likely won't witness this collision's climax, its certainty frames a profound truth: the universe doesn't stand still. Even the mightiest galaxies are temporary patterns in an ever-shifting cosmic web, destined to merge, fade, or transform in ways we're only beginning to imagine. The Whirlpool Galaxy spins like a celestial jewel, its spiral arms awash with newborn stars and glowing nebulae. But just off its shoulder, a smaller companion galaxy twists in its gravitational grip, locked in a dance that's reshaping them both. Known as NGC 5195, this satellite galaxy isn't just a passive neighbor, it's a key player in one of the most dramatic makeovers in the cosmos. Over hundreds of millions of years, the Whirlpool's immense gravity has been pulling its companion apart, stretching it into a chaotic stream of stars and gas that now loops around the larger galaxy like a cosmic lasso. What makes this duo so mesmerizing isn't just their beauty, it's the way they reveal gravity's patience as an artist. Every close pass between the galaxies tugs on their structures, warping spiral arms, igniting bursts of star formation, and flinging stellar material into the void. The Whirlpool's iconic arms, so perfectly symmetrical in images, are actually asymmetrical, their shape distorted by the companion's relentless pull. Meanwhile, NGC 5195 itself is being unraveled, its stars scattered into a long, shimmering tidal tail that stretches across 40,000 light-years. This isn't just destruction, it's transformation. The same forces tearing the smaller galaxy apart are also funneling fresh gas into the whirlpool's disk, fueling new generations of stars and painting its spiral arms with brilliant blue clusters. But the real magic lies in the details. Peering at the contact point between the two galaxies, astronomers have spotted knots of intense star formation regions where gas compressed by gravitational tides has collapsed into fiery stellar nurseries. These knots are like cosmic breadcrumbs marking the path of the companion's slow-motion disintegration, and because the whirlpool is relatively close, just 23 million light-years away, we can study this process in unprecedented clarity, watching as gravity sculpts galaxies in real time. Here's the twist: this dance isn't unique. Galactic mergers and interactions are common throughout the universe, but the whirlpool and its companion offer a rare snapshot of the early stages of such a collision. Unlike the cannibal galaxy NGC 1316, where mergers are near completion, here we see the prologue, the first act of a story that will unfold over billions of years. Eventually, NGC 5195 will be entirely absorbed, its stars assimilated into the whirlpool's halo, its gas recycled into new stars and planets. The whirlpool itself may lose its elegant spiral structure, reshaped into something new by the encounter. Yet for now, they remain a matched pair, a living textbook on how galaxies evolve not in isolation, but through relentless gravitational conversations. Their interaction is a reminder that even the grandest cosmic structures aren't static, they're dynamic, ever-changing, and forever intertwined with their neighbors. And somewhere in their swirling embrace, we catch a glimpse of our own galaxy's future, a hint of the transformations awaiting the Milky Way when Andromeda finally arrives. Sometimes the most groundbreaking discoveries in astronomy come from cosmic wreckage, and few collisions have reshaped our understanding of the universe like the Bullet Cluster. Picture two massive galaxy clusters, each containing hundreds of galaxies, slamming into one another at speeds exceeding millions of miles per hour. The aftermath of this violent encounter, located 3.8 billion light-years away, didn't just leave a mess of stars and gas. It revealed dark matter's shadowy fingerprints in the clearest way scientists have ever seen. Here's what makes this collision so extraordinary. When these clusters collided, their hot gas, the visible matter, piled up in the center like two trucks crashing head-on, creating a shockwave detectable in X-rays. But something eerie happened to the cluster's mass, mapped through gravitational lensing, the way their gravity bends light from more distant galaxies. The bulk of the mass didn't stay with the gas. Instead, it sailed right through the collision, trailing behind like an invisible ghost. That discrepancy, gas in one place, most of the mass in another, was the smoking gun, proof that dark matter, whatever it is, doesn't interact with ordinary matter except through gravity. It's as if two crowds of people ran into each other, but their shadows kept walking unfazed. The implications of this discovery can't be overstated. Before the Bullet Cluster, dark matter was a compelling theory backed by indirect evidence: galaxies rotating too fast, cosmic microwave background patterns. But here was direct observational proof that dark matter exists as a separate, tangible component of the universe, not just a flaw in our equations. It behaved exactly as simulations predicted, collisionless, indifferent to electromagnetism, and fundamentally unlike anything made of atoms. Yet the Bullet Cluster isn't just about confirming dark matter. It's also a thorn in the side of alternative theories. Some physicists had proposed tweaking Einstein's theory of gravity, modified Newtonian dynamics, or meant to explain galactic rotation without invoking invisible matter. But the Bullet Cluster's clean separation of mass and gas is nearly impossible to explain without dark matter's gravitational pull. It's as if the universe handed us a controlled experiment, isolating gravity's effects in a way no lab ever could. What's equally fascinating is how rare and precious such collisions are. Galaxy clusters are the largest gravitationally bound structures in existence, and their mergers unfold over billions of years. Catching one mid-collision with features so distinct is like stumbling upon a fossil at the exact moment it's being formed. The bullet cluster's pristine state lets astronomers measure dark matter's distribution with precision, revealing it isn't just a diffuse halo but clumps along filaments scaffolding the cosmic web. But the mystery deepens when you ask, what is dark matter made of? The bullet cluster confirms its existence but doesn't answer its nature. Is it a sea of undiscovered particles like WIMP or actions, or something even stranger, a shadow universe with its own rules? Every new observation, like similar collisions found since, adds pieces to the puzzle while keeping the big picture tantalizingly out of reach. Perhaps the most profound lesson of the bullet cluster is how much we still don't understand about the cosmos. It's a reminder that the universe's greatest truths often hide in plain sight, waiting for the right collision, the right observation to tip their hand. And somewhere in that invisible mass, in the gaps between what we see and what we know must be there, lies the next revolution in physics. The bullet cluster isn't just a relic of a past collision, it's a beacon, guiding us toward the dark heart of the universe's deepest secret. Drifting through the void like a celestial tadpole frozen mid-swim, the Tadpole Galaxy presents one of the most striking examples of gravitational artistry in the known universe. This distorted spiral galaxy, located 420 million light-years away in the constellation Draco, stretches an astonishing 280,000 light-years from end to end, nearly 3 times the diameter of our Milky Way, with its most spectacular feature being a gargantuan tail of stars and gas arcing behind it like a cosmic comet's trail. This isn't just random asymmetry, it's the aftermath of a violent gravitational encounter that warped an ordinary galaxy into this extraordinary shape, giving astronomers a front-row seat to the chaotic ballet of galactic collisions. The tadpole's distinctive tail formed when another galaxy passed too close, its gravitational pull stretching the tadpole's spiral arms like taffy, while flinging a stream of stars and gas into intergalactic space. Imagine 2 dancers spinning past each other, their outstretched arms briefly linking before momentum whips one away, leaving strands of fabric trailing behind. Except here, the fabric is entire star clusters, and the dance unfolds over hundreds of millions of years. What makes this collision particularly fascinating is how pristine the tail remains. Unlike the messy debris fields seen in advanced mergers, the tadpole's tail is a clean, coherent structure, suggesting we're witnessing the immediate aftermath of the encounter, frozen in cosmological time. Inside the tail lies another revelation: blue knots of intense star formation, where gas compressed during the collision ignited bursts of newborn stars. These stellar nurseries are laboratories for understanding how galactic interactions trigger star birth, demonstrating that chaos doesn't just destroy, it creates. Meanwhile, the tadpole's main body shows signs of disturbance, with its spiral arms asymmetrically warped and its core possibly hosting a rejuvenated supermassive black hole, stirred to activity by the influx of fresh gas. But the real treasure of the Tadpole Galaxy isn't just its appearance, it's what it represents. Most galaxies in the universe's early epochs were smaller and more prone to collisions, meaning objects like the tadpole were likely commonplace. Today, it serves as a time capsule, showing us how these ancient interactions built up modern galaxies through a cycle of destruction and rebirth. Its tail, though spectacular, is temporary. Over billions of years, gravity will either reel the material back in or scatter it forever into the void. For now, the tadpole remains a fleeting masterpiece, a reminder that even the grandest cosmic structures are never static, only ever-changing portraits in an infinite gallery of gravitational art. At the center of most galaxies, supermassive black holes lurk like sleeping giants, but in one extraordinary corner of the universe, a black hole has awakened to forge a structure so rare astronomers once doubted it could exist. Meet the Ring of Fire galaxy, officially known as NGC 1672, where a perfect circle of newborn stars blazes just 3,000 light-years from the crushing grip of a supermassive black hole. This isn't just unusual, it's nearly impossible. Black holes are supposed to be destroyers, their gravitational tides ripping apart anything that ventures too close. Yet here, against all odds, stars are being born in a shimmering ring that dances perilously close to the cosmic abyss. The ring's existence defies conventional wisdom. Normally, the intense gravitational shear near a black hole should prevent gas from cooling and collapsing into stars. Imagine trying to build a sandcastle in the middle of a hurricane. That's the chaotic environment stars face this close to a black hole's maw. But in NGC 1672, something extraordinary happened. Vast streams of cold gas, likely funneled by the galaxy's unique structure, managed to flow inward until they reached a sweet spot just beyond the black hole's most violent tides. There, the gas pooled into a dense, rotating disk, shielded just enough to allow gravity to work its magic, knitting atoms together into brilliant new stars. The result, a celestial firestorm where stellar nurseries glow like embers encircling a dark heart. What's even more baffling is the ring's stability. Star-forming regions this close to a black hole should be fleeting, their gas either swallowed or blown away by radiation. Yet observations suggest this ring has persisted for millions of years, possibly replenished by fresh gas spiraling in from the galaxy's outer reaches. It's like a cosmic fountain where material continually cycles inward, feeding the ring's fiery rebirth. Some theorists speculate the black hole itself might be indirectly nurturing this process. Its occasional outbursts of energy could compress surrounding gas clouds, triggering waves of star formation even as it devours other matter. The Ring of Fire galaxy isn't just a cosmic oddity. It's a key to unlocking how black holes and galaxies co-evolve. Most models assume black holes suppress star formation in their vicinity, yet here we see the opposite, a black hole that might, under the right conditions, act as a midwife to new stars. This revelation forces astronomers to reconsider the delicate balance between creation and destruction in galactic cores, and whether similar rings might exist elsewhere, hidden by distance or dust. Perhaps the most humbling lesson of NGC 1672 is how much we still don't understand about the universe's extremes. For every rule we establish, black holes tear gas clouds apart, stars can't form in chaos. The cosmos delivers an exception, proving that nature's creativity knows no bounds. The Ring of Fire galaxy stands as a glowing testament to that ingenuity, a place where destruction and creation orbit hand in hand, rewriting the rules as they go. Some cosmic collisions leave behind wreckage, others birth stunning new forms, and the Medusa merger is nature's finest example. This tangled dance of two galaxies, officially known as NGC 4194, paints a portrait of chaos and creation 600 million light-years away in the constellation Ursa Major. Once separate spirals, these galaxies now intertwine like cosmic serpents, their distorted arms weaving streams of stars and gas into a luminous, Medusa-like tapestry. But what makes this merger extraordinary isn't just its beauty, it's the frenetic stellar rebirth erupting from the wreckage, proving destruction and genesis are two sides of the same cosmic coin. At the heart of the Medusa merger, gravitational tides have compressed vast gas clouds, igniting one of the most intense starbursts ever observed. Picture two hurricanes colliding. Their winds don't just cancel out, they create towering new vortices. Similarly, as the galaxy's spiral arms clash, shockwaves ripple through their interstellar gas, triggering avalanches of star formation so fierce they outshine entire galaxies. The brightest knots in this firestorm, captured in vivid detail by Hubble, are superstar clusters, dense gatherings of 1 million young stars packed into regions barely 100 light-years wide. To stand on a planet near one would mean a night sky filled with thousands of stars as bright as Venus, their combined light casting permanent shadows. Yet the real magic lies in the merger's asymmetry. Unlike neat textbook collisions, the Medusa merger is lopsided. One galaxy's core remains intact, while the other has been stretched into a serpentine tail studded with newborn blue stars. This imbalance reveals a critical truth about galactic mergers. Their outcomes aren't uniform. The angles, speeds, and compositions of the colliding galaxies sculpt unique final forms, turning each merger into a cosmic fingerprint. Here, gravity has sculpted a structure resembling the mythical Medusa's hair, with tendrils of stars and dust writhing outward like luminous snakes frozen mid-strike. What's startling is how this violence fosters life. The merger's turmoil has enriched the interstellar medium with heavy elements forged in supernova, seeding future generations of stars with the building blocks for planets and potentially life. Meanwhile, the supermassive black holes at both galaxies' cores, though still separate, are sinking toward each other in a slow death spiral. When they finally merge billions of years from now, their union will unleash gravitational waves powerful enough to briefly outshine every star in the galaxy combined. Medusa's greatest lesson might be its impermanence. Today's dazzling starburst will eventually exhaust its fuel, leaving behind a featureless elliptical galaxy, a quiet tombstone marking the fiery union that birthed it. But for now, this merger is a living laboratory, showing us how the universe recycles chaos into structure, destruction into creation. It's a reminder that even in the darkest depths of space, cataclysm and beauty are eternally entwined. Drifting through the constellation Cassiopeia like a celestial spectre, the Ghost Nebula is a hauntingly beautiful cloud of gas and dust, glowing faintly under the relentless bombardment of radiation from a nearby star. This eerie formation, officially known as IC63, isn't just a random wisp in the cosmos, it's a dynamic snapshot of stellar evolution, a fleeting moment in the life and death of stars. Imagine a delicate veil of hydrogen gas, sculpted by invisible forces into tendrils that stretch across light years, backlit by the fierce ultraviolet glare of its celestial tormentor. The result is a ghostly apparition that seems to flicker against the darkness of space, earning its supernatural nickname. What makes the ghost of Cassiopeia so mesmerizing isn't just its ethereal glow, it's the violent interplay between creation and destruction unfolding within it. The nebula's delicate filaments are being shaped and simultaneously eroded by Gamma Cassiopeiae, a massive, rapidly spinning star located just 4 light-years away. This star isn't just bright, it's a cosmic blowtorch, unleashing torrents of high-energy radiation and stellar winds that push against the nebula's gas, compressing some regions into dense knots while scattering others into the void. It's like watching a sand sculpture battered by hurricane-force winds, with some grains clumping together while the rest are swept away. But hidden in this chaos lies a deeper story. The Ghost Nebula is a reflection nebula, meaning it doesn't emit its own light. It shines by reflecting and scattering the light of nearby stars. The blue hues dominating its structure come from starlight bouncing off dust grains, while the faint red glow comes from hydrogen gas excited by ultraviolet radiation. This interplay of color and light reveals the nebula's composition, a mix of raw materials left behind by previous generations of stars, now being recycled into something new. The real magic, though, happens in the shadows, within the densest pockets of the Ghost Nebula, shielded just enough from Gamma Cassiopeia's fury. Gravity is quietly at work. Gas and dust accumulate, growing denser and hotter until, under the right conditions, new stars may ignite. It's a cosmic irony. The same radiation tearing the nebula apart is also creating the conditions for rebirth. This delicate balance between destruction and creation is a hallmark of star-forming regions, but the Ghost Nebula presents it with rare clarity, showcasing the universe's cyclical nature in vivid detail. Yet the Ghost's fate is already sealed. Given enough time, Gamma Cassiopeia's relentless energy will disperse the nebula entirely, scattering its gas into the interstellar medium where it might one day coalesce into new nebulae, new stars, even new planets. What we're witnessing is a transient masterpiece, a structure that, like all things in the cosmos, is temporary. For now, it lingers, a shimmering reminder that even in the void of space, nothing is ever truly still. The ghost of Cassiopeia is more than just a pretty spectacle. It's a lesson written in starlight, teaching us that the universe is always in motion, always changing, and always transforming destruction into the seeds of new beginnings. Deep in the constellation Cancer, a world unlike any other in our solar system glitters with unearthly brilliance, a planet so dense and carbon-rich that scientists believe substantial portions of it may have crystallized into diamond. Meet 55 Cancri, a super-Earth twice as wide as our own world and 8 times as massive, orbiting so close to its host star that a year lasts just 18 hours. Surface temperatures here soar above 4,000 degrees Fahrenheit, hot enough to vaporize rock, yet paradoxically perfect for forging the universe's most coveted gemstone on a planetary scale. What makes this diamond planet extraordinary isn't just its potential bling. It's the window it offers into planetary extremes. Traditional planet formation models built on our carbon-poor solar system never predicted worlds like this. 55 Cancri likely formed in a protoplanetary disk teeming with carbon, where instead of silicon and oxygen dominating the chemistry, as with Earth's crust, carbon became the cosmic architect. Under intense heat and pressure within the planet's mantle, that carbon may have compressed into layers of diamond hundreds of miles thick, interspersed with graphite and other exotic forms. Picture a planetary core not of molten iron, but of crystallized carbon, with diamond icebergs floating in seas of molten carbon-rich rock. Yet the diamond hypothesis isn't without controversy. Alternative studies suggest the planet's carbon might manifest as vast reservoirs of graphene or even stranger phases like metallic carbon, where atoms arrange into conductive lattices under extreme pressure. There's also the enigma of its atmosphere. Hubble observations hint at traces of hydrogen cyanide, a molecule rich in carbon but also startlingly toxic. If confirmed, this could imply an atmosphere unlike any known, where the very air is laced with the building blocks of organic chemistry, forged in a furnace of diamond rain. The broader implications are staggering. If carbon-rich planets like this are common, it suggests planetary systems can form with chemistries radically different from ours, worlds where mountains might be made of diamond, rivers of tar, and sand of graphite. Some astronomers speculate that in cooler carbon planets, buried diamond layers could even act as thermal insulators, creating subsurface habitats for exotic life forms. While 55 Cancri is far too hostile for life as we know it, its existence proves the universe crafts planets from recipes we've only begun to decode. Perhaps most humbling is what this world reveals about our cosmic neighborhood's mediocrity. Our sun, it turns out, is somewhat carbon-poor compared to many stars. Around stars richer in carbon, entire systems of diamond planets might exist, rewriting the definition of terrestrial. 55 Cancri isn't just a curiosity, it's a wake-up call, proving that the universe's planetary palette is far wilder than we ever imagined. And somewhere in its glittering depths, we might just find the key to understanding how chemistry shapes not just worlds, but the possibilities of existence itself. Picture a star not bound to any galaxy, sailing through the void like a cosmic castaway. This is the haunting reality of intergalactic stars. These solitary wanderers, untethered from galactic arms or clusters, drift in the immense darkness between galaxies, their light faint but defiant against the blackness. Some were violently ejected from their homes during galactic collisions or close encounters with supermassive black holes, flung into the abyss like stones from a slingshot. Others might have formed in the loneliest of nurseries, coalescing from rogue gas clouds stranded in intergalactic space, far from any galaxy's gravitational embrace. Take HV1, a massive star racing through the emptiness between the Milky Way and Andromeda at over 1 million miles per hour. Its speed and trajectory suggest it was hurled outward by a close brush with the black hole at our galaxy's core, a gravitational kick so powerful it escaped the Milky Way entirely. Now it burns alone, its brilliance visible only because of its sheer luminosity, a beacon marking a path no other star might follow for millennia. But not all intergalactic stars are exiles. Some may have formed in the sparse, forgotten gas filaments of the cosmic web, where densities were just high enough for gravity to spark fusion but too low to build galaxies. These orphan stars challenge our understanding of star formation, proving that the universe can forge suns even in its emptiest reaches. Their light, though dim, stitches together the voids, hinting at vast, unseen networks of matter flowing between galaxies like invisible rivers. What's truly humbling is the scale of their isolation. An intergalactic star might travel for billions of years without approaching another celestial object, its planets, if it has any doom to eternal night. Yet these wanderers aren't just curiosities, they're cosmic tracers. By mapping their paths, astronomers reconstruct the violent histories of galaxies, piecing together collisions and ejections that happened long before Earth formed. Others, like hypervelocity stars, might even carry clues about dark matter's distribution, their trajectories warped by invisible halos we can't otherwise detect. And then there's the eerie possibility that intergalactic space could harbor rogue planets, torn from their parent stars and drifting frozen in the dark. If life exists on such worlds, it would evolve under skies devoid of neighboring suns, with only the faint glow of distant galaxies to mark the passage of time. It's a chilling thought entire civilizations, if they exist, might rise and fall in total isolation, their stories forever untold. Yet these lonely stars might also be pioneers. In the far future, as galaxies grow more distant due to the universe's expansion, intergalactic stars could become the only lighthouses left, outliving their galactic cousins as the cosmos cools and darkens. For now, they drift silent witnesses to the universe's unyielding vastness, reminding us that even in the crowded cosmos, solitude is just another shape the darkness takes. From the Great Attractor's invisible pull to the diamond-studded plains of 55 Cancri, these 25 cosmic enigmas prove one thing: the universe delights in defying our expectations. They challenge the limits of human knowledge, forcing us to rewrite the rules of physics, rethink the nature of gravity, and confront the humbling truth that we've only glimpsed a fraction of what's out there. Whether it's the eerie perfection of Hoag's object, the violent beauty of the Medusa merger, or the chilling emptiness of the Boot's void, each structure whispers a tantalizing question: what else is hiding in the dark? These wonders aren't just scientific curiosities, they're invitations to marvel at the universe's boundless creativity, to stay curious in the face of the unknown, and to remember that every answer we uncover only reveals deeper mysteries. The cosmos doesn't exist to be easily understood. It's a grand, ever-evolving puzzle meant to inspire awe, not just answers. Now, we'd love to hear from you. Which of these cosmic marvels left you breathless? Was it the haunting glow of the Vorwurps, the galactic carnage of the Cannibal Galaxy, or something else entirely? Drop your favorite in the comments below. Let's keep the conversation as infinite as the universe itself. And remember, the next time you look up at the night sky, know that the real magic lies not in the stars you can see, but in the countless wonders still waiting to be discovered.